Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its offering of services and products for the implementation of artificial intelligence models for robust design of resilient supply chains based on parallel and distributed analytics, or artificial brains for Industry 4.0. Resilient supply chains. Resilience is the ability to resist and recover from strong disturbances or disasters, to continue with its normal operation and ensure the fulfillment of its functions. Some extreme events that seriously affected supply chains during the period 2010 to 2012. Volcano in Iceland, volcanic ash in the atmosphere, forced the closure of much of Europe's airspace for several days, causing major disruptions to air cargo shipments. Earthquake and tsunami in Japan, they caused devastation in Japanese productive infrastructure that led to the disruption of multiple global supply chains, because many factories were temporarily inoperative. Floods in Thailand, several high-tech supply chains were severely affected, causing disruptions in the supply of key components in the computer industry, as hard drives. Shortage of rare materials. The Chinese government imposed restrictions on the export of rare materials, meaning key electronic components could not be manufactured. In 2011, China accounted for about 90% of the world's supply of rare materials, and nylon shortage. An explosion at the Evonik Industries factory in Germany led to a worldwide shortage of CDT, a key ingredient in nylon, which is widely used for component manufacturing in the global automotive industry. These extreme events taught everyone involved that risks should be considered by design, involving in the process scientific methodologies for the management of operational risks and financial risks. These risks may be managed so that the company has a supply chain that operates very well most of the time, and that can react to unexpected events of negative impacts. Therefore, the mathematical models to be used cannot stop looking at these aspects, because the current technological state allows to prepare the companies to manage risks in the most intelligent way possible. It is worth quoting Peter Bernstein, who in his book, Against the Gods, The Remarkable Story of Risk, says, "The revolutionary idea that defines the boundary between modern times and the past is the domain of risk management, the notion that the future is more than a whim of the gods, and that men and women are not passive to nature. The essence of risk management lies in maximizing the areas where we have some control over the outcome, while minimizing the areas over which we have absolutely no control, and the link between cause and effect is unknown." Framework for Supply Chain Design Optimization. The value chain of an industrial company is usually composed of two chains, supply and demand. The supply chain looks inside the company, and usually focuses on prescriptive analytics models, optimization. The demand chain looks outside the company, and usually focuses on predictive analytics models, forecasting of the clients and the competitors. HI's overall approach is to connect predictive and prescriptive analytical models, involving an integrated, multidimensional holistic view, across space and time, of the entire supply chain. Scope of the supply chain design. It allows studies to be carried out to optimally coordinate the long-term decisions associated with the design and simulated optimal operation of the supply chain for localization of new infrastructure, and expansion and/or modernization of current infrastructure. It allows studies to determine the optimal strategy to operate the supply chain, within which can be cited assignment of service areas to distribution centers, determination of inventory management policies, and determination of transportation resource management policies. The objective will be to minimize investment costs, plus the expected value of future operating costs. Must include considerations for controlling financial risk. Decisions are related to answering questions, such as how many, when and where should production plants be located? How many, when and where should production lines be located? What infrastructure should be owned, and which should be rented to third parties? What products and in what quantities should be produced in each plant, and in each production unit? Which supplier, and in what quantities, should serve each plant? Which plant, and in what quantities, should serve each distribution center? How much inventory of raw materials, products in process, and finished products should be maintained in each storage center? The main benefits are: maximizes the expected profit corresponding to investment plans. It controls financial and operational risks, allowing more rational, accurate, and robust decisions, and it allows a rapid analysis of scenarios of the decision-making environment. In 2005, Leon Sters of Deloitte at a conference called "How Get More Out of Your Supply Chain? Supply Chain Planning and Optimization." He presented the impact of implementation of what at the time were called APS, Advanced Planning and Scheduling Systems. APSs are computer platforms, based on the intensive use of mathematical optimization. The scope of implementation of an APS significantly impacts cost savings. In all hierarchical stages of the decision-making, strategic, tactical, and operational. Sters affirms that the greatest economic impact is achieved in strategic decisions, and that it is decreasing as we get closer to the operation. This is evident if the industrial infrastructure is built in the wrong place, and the portfolio of final products is poorly selected, little can be recovered by producing and transporting very well the products that should not be produced in the wrong places. Going back a strategic decision may be impossible. Mathematical modeling of the supply chain network design involves at least 3 types of models. Investment coordinates the logic of investments in the present and in the near future. Operations estimates operating costs and operating policies, which are derived from investments, and financial coordinates the cost of investments and operations with financial flows to ensure their viability and financial convenience. Additionally, it must control the financial risks due to investments. The Decision Support System, DSS, for design and planning of industrial supply chains will be called SCD. SCD must be made up of multiple models that interact with each other. Models may be solved in 2 ways. Coordinated, independent models that share results with each other, according to a logical data flow. Integrated, the models are integrated into a single mathematical model that is solved as a single mathematical problem. The best way is integrated, considering that it can solve the holistic optimization model until it reaches the optimal solution. The first model will be called LogFin. It is oriented to define the investments to be made in infrastructure necessary for production. It corresponds to a dynamic model that defines, for each period of the planning horizon, the investments to be made, and the network for short-term operation. As input parameters, it should consider the costs of investment, rate of return on capital, the costs of loans, payment period, and other financial considerations. Model constraints are related to investment logistics and financial risks. The main results of the model are NPV, net present value, of the investments, VAR, value at risk, cash flow, and network design for the first periods. The second model will be called SANDOP. It is aimed at simulating industrial operations for each possible network proposed by the investment model, LogFin. As input parameters, it should consider, at least, the forecast of demand of final products, raw material supply, operational costs, and sell prices. The model can be extended to consider other aspects such as technological innovation that affects the productivity of processes, new technologies, which may affect market prices, and others that are considered convenient. In general, all input parameters are uncertain, and it is appropriate to consider that this makes a stochastic programming model based on scenarios. This characteristic makes the LogFin model a coordinator of the evaluation of the scenarios to be considered in SANDOP. It corresponds to a dynamic model that defines, for each period of the planning horizon, the industrial operations, and the storages of materials. In certain cases, it may not be necessary to consider product storage, because it may have little impact on investment costs, and additionally, it may be considered that its offer is always provided by the market with stable prices. This is not the case for oil storage, where the market prices and the supply of oil and gas is uncertain with high volatility. The constraints of the model are related to the industrial production process. Normally, there are several alternatives to simulate this process. At one extreme, we may formulate a very simple model, perhaps a few aggregate equations, that synthesize the process. At the other extreme, we may formulate a detailed model that simulates the processes with great certainty. The decision is of the modeler. What is true is that the available computer technology, computers plus solvers, allows very advanced models in this aspect. Therefore, the level of detail will grow exponentially in the next years. The main result of the model is the operational simulation for each period for each scenario. Data that are necessary to evaluate the future cost function that generate the decisions of the present. The third model will be called ALM. Its objective is to simulate the assets and liabilities management, ALM, considering the results provided by LogFin and SandOp models. ALM is a modeling consolidated methodology that focuses on the financial modeling of companies. Its growth is generated at the end of the past century, in the financial sector, as a result of the Basel Accords. The minimum ALM modeling should be oriented to evaluate the NPV, for a pre-established ROI, return of investments. It will provide the financial statements, balance sheet of assets, liabilities and equity, income statement, profit and loss, after tax, royalties, and other contributions, and cash flow. Extended ALM modeling may include investments in alternative assets and liabilities, payment of dividends, capital repatriations, capital flow, and multiple currencies. In healthy logic, this model must be the coordinator of the holistic investment process, since it is the financial vice presidencies of the organizations responsible for endorsing investments in production assets. The results of the holistic optimization process are probability distribution functions for the primal variables and the dual variables of all DSS models. For example, the NPV. In simpler modeling, these distribution functions are obtained using spreadsheet simulation models. The results are not comparable because of the methodological difference in the approach. Investment projects. Infrastructure expansion projects provide the possibility of increasing capacity of existing infrastructure through extensions or upgrades of existing infrastructure, or creating new capacity through new installations. The optimal location of the infrastructure and the allocation of resources will be related to decisions aimed at minimizing costs or maximizing benefits, with the overall objective of maximizing utility for each dollar invested. Investment project modeling considers the following types: installation of additional capacity, infrastructure on installation, and infrastructure modernization. In SCD, the investment projects are defined as sum of infrastructure installations. For example, in the electric sector, a project may be reservoirs plus hydraulic plants plus canals plus thermal plants plus transmission lines plus gas pipeline sections plus energy storages. And the development of the project is organized by alternatives and stages. The example is an investment project with three mutually exclusive alternatives: hydro plant, solar farm, or eolic farm. And the alternative of the hydro plant must, or can, be carried out in three stages. This type of modeling facilitates, for the optimization model, to find the best solution, since otherwise it would be necessary to evaluate a combinatorics of alternatives, many meaningless, to select the infrastructure installations to be carried out. The solution will be to select an alternative to carry out the project. Under a real options approach, the solution could be to do nothing, and wait for the future to rethink the decision. The design of a distribution chain does not have to involve infrastructure installations, because the network connectivity may be the objective of optimization. In this case, coming from reality, the decision maker is a company producing appliances, in Asia and in the USA, which is interested in defining the distribution chain to serve the Colombian market. The first decision is to define the policy of the dispatch of products to Colombian ports. Two alternatives should be analyzed. Dispatch directly to a port in the Pacific Ocean, Buenaventura, and to another port on the Caribbean Sea, Cartagena, and from these ports, begin distribution in Colombia, or already in Colombia, the national distribution chain must be designed, which must be integrated through a network of warehouses, cross-docking platforms, transport modes, and retailers. The optimal solution provided by the SCD model was use Panama as a hub for container cross-docking, dispatch to Cartagena and Buenaventura the containers classified, according to the orders of the distributors, use 2 warehouses in Cartagena and another in Cal, remove cross-docking platforms, and deliver from direct warehouses to distributors. 2 decision criteria must be considered. Customer service related with service time, in days, and or stock out probability, and financial aspects related with maximize profits, or minimize costs. This is a multi-criteria optimization problem, whose characterization is presented in the graph. When the delivery time is reduced, the cost increases. This means that it is not possible to optimize the 2 criteria simultaneously, which implies a compromise solution, which balances the 2 criteria. This Pareto curve is necessary for decision making. If it is known, it can be supplied directly, otherwise the mathematical model must build it. The problem of customer service originates in the uncertainty of demand for final products. The production time, LP, which must consider the lead time of purchases, of inputs and raw materials, and the lead time of sales, LD, which depends on the distribution network. There are multiple indicators to measure the service level. For example, the level of customer service can be defined, setting the alpha probability of not attending demand on time. From the alpha probability, the expected lead time, and the safety stock, may be estimated. For this, it is necessary to know the probability distribution function of the demand. Safety stock and delivery time directly affect inventory policy costs that are part of the future operating costs of the productive system. The inventory policy must be applied in distribution centers that serve customers. Assuming that the demand of customer I follows an independent multivariate normal probability distribution, with mean mu and standard deviation rho I. The stock safety is equal to alpha probability percentile, multiplied by the standard deviation of customer demand. If multiple customers are served, each from a distribution center, the total security level will be equal to the sum of the standard deviations of customers' demand, multiplied by the alpha probability percentile. But, if all clients are served from only one distribution center, the security level is equal to the square root of the sum of the standard deviations of customer demand, multiplied by the alpha probability percentile. From the point of view of safety stock, the second alternative is less expensive than the first, and use one distribution center with maximum capacity. However, the first should have lower transportation costs, and smaller distribution centers. And the delivery time is affected by the stock out probability, and the distribution chain structure. This analysis demonstrates that customer service management costs depends on the network topology, which is one of the objectives of supply chain design models. The costs, direct and indirect, that make up the objective function are: investments depend on the specific projects. The investment plan must be checked with financial vice presidency. Operating costs function of the supply chain structure. Inventory costs function of stock out probability. Inventory level depends on the number of customers served by a distribution center, and transportation costs function of the supply chain structure. Stages of supply chain design. The process of strategic decisions should not be visualized as the run of a magic artificial intelligence model, which in an instant, magically, produces the best decision for the company. It is a cyclical, iterative process in which mathematical models serve to produce knowledge about the company and its environment. Normally 2 stages should be considered. Project screening aims to select alternatives for decisions, in such a way as to eliminate those that cannot be optimal, and leave those that may be the best solution. Detailed assessment aims to disaggregate information, so that in the end the mathematical model produces the correct evaluation of the alternatives that finally pass the screening process. The information generated in the process opens the mind of the decision makers to alternatives that perhaps they have not thought of, because they haven't been able to see the whole system holistically. To understand the screening process, we can consider the cost of an industrial equipment. Normally, the capacity to be installed is not a continuous variable, it is discrete, because equipment manufacturers commercially offer equipment with predefined capacities, for example, generation turbines of 10 megawatts or 50 megawatts, until reach their maximum capacity. This function is associated with scale economies. Then, for each capacity there is an associated cost predefined by the manufacturer. Knowing the price lists of all manufacturers, for all the equipment offered, may be a complex process, perhaps confidential. If this modeling alternative is chosen, for all the possibilities of equipment, those that will be bought, and those that will not be bought, the mathematical model may lead to a combinatorial problem of great dimensionality, perhaps very difficult to solve. The selection process may involve approximating the curve of all manufacturers, or perhaps reducing it to an approximate curve for the type of equipment. An approximate piecewise curve for cost of continuous capacities eliminates the combinatorial character of the mathematical problem, and it can produce an idea of what is the range of capacities that the model considers optimal. Therefore, decision makers will know what detailed information they should get. In the initial phases of the screening process, thicker approximations can be used, as would be the case of a linear approximation, based on a fixed cost plus a variable cost. This can be modeled linearly, without complication. In conclusion, it can be affirmed that the process of designing supply chains, using artificial intelligence methodologies, is a process of knowledge generation, which must combine the strength in mathematical modeling, with the deep knowledge of decision makers, about the specific supply chain. Optimization under uncertainty and risk management. Optimization under uncertainty is integrated by: first, robust optimization when the parameters of the model are characterized based on variation ranges, and the objective of the model is to produce the best solution considering the worst situation for the occurrence of the parameters. Second, stochastic optimization when model parameters are characterized probabilistically and therefore all results can be associated with empirical probability distribution functions that depend on the risk management policy. The stochastic optimization process. It is composed of 3 stages: identification of the stochastic process model, implementation of a synthetic scenario generator, and design and implementation optimization stochastic model for decision support. Stochastic optimization implies the definition of the decision-making process, definition of the uncertainty dimensions and the stochastic processes associated with parameters, the risk management policy, and the approach to use for the computational solution. There are multiple decision criteria, objective functions, that can be integrated into models which are associated with the risk management policy and risk position, prone or adverse, of the decision maker. Scientific, financial and operational risk management is the true benefit provided by stochastic optimization models. The complexity of this problem lies in its bi-criterion nature: maximizing the expected revenue and minimizing the risk assumed in decisions under uncertainty. This is summarized in the Pareto curve: risk versus expected revenue, which is the final information produced by mathematical models to support decision-making. Since the end of the past century, the mathematical formulations to control the CARE in mathematical programming models were developed. Rockefeller and Yuri Yasev, 2002, Conditional Value at Risk for General Loss Distributions. These methodologies, for the scientific financial risk management, have been included in high-power models to control/manage financial risks and operational risks. High proposes that the approach of the financial risk control policy be it solve a problem that maximize expected profits, subject to CVAR costs, less than or equal to 0, or CVAR revenue, greater than or equal to 0. Optimization is everywhere,